In this video, I want to extend our discussion of one-dimensional coordinate systems to two-dimensional Cartesian coordinate systems. And for the most part, that's just another axis which we get to choose, but I'm also going to add a bit of a twist. All right, so first of all, let's look at exactly the same problem we started with last time. We have this ball rolling across the table. We have a picture of it for each second. In fact, that's silly. Let's do t is equal to 0, 1, 2, and 3. Of course, it starts at that first location. But instead of just doing it's one-dimensional motion, but instead of having a one-dimensional coordinate system, we're going to have a two-dimensional coordinate system. We're going to choose the 0 of the x-axis on the edge of the table, like we did before, but we're going to put the 0 of the y-axis here on the ground. So this will I'll say the positive x-axis in centimeters goes off to the right, and we're going to say that the positive y-axis in centimeters goes up. I'm not necessarily saying you should do this. This is one-dimensional motion. I would probably choose a one-dimensional coordinate system. But I want to show just the simplest example now what a two-dimensional coordinate system looks like. We still get to choose the 0. We get to choose the dimensions. And for a Cartesian coordinate system, we want to make sure that our two dimensions are orthogonal. So like before, we had, along the x direction, we had 5 and 15, 25 and 35 centimeters for each of the seconds. And let's say that, given this coordinate system, we measure this location to be 60 centimeters. So now, when we sort of go to a tabular representation of what's going on, x is equal to 0. We saw this before as 5 centimeters. At 1 second is 15. At 2 seconds is 25. And at 3 seconds is 35. But that's not 9 centimeters, all of these. But we also need then its location along the y-axis, which, for this example, is 60 at every point in time. So y is equal to 0 is 60 centimeters. Y at 1 is 60 centimeters. Y at 2 is equal to 60 centimeters. And y at 3, 60 centimeters. Not particularly interesting example, but I want to highlight just the idea that you now have to keep track of each coordinate separately. If we want a graphical representation of this information, now this is not the entire position, but just the x-coordinate of the position as a function of time. So x in meters, t in seconds, 1, 2, 3, and there's 10, 20, 40. So it started at 5, and then at 1 is 15, 25, 35. If this are 10, 20, 30, 40. So this is now the graphical representation of the x-coordinate of the motion. So if we were to look at the graphical representation, t in seconds, of the y-coordinate, well, here's 60, and we don't really need much else there, do we? T is equal to 1, 2, 3, 1, 2, 3, straight, flat line. So with no motion in the y direction, we have a flat straight line of the y coordinate in this particular coordinate system. Okay, so that was kind of simple, but just we have to keep track of it separate. I want to throw a little wrinkle into this. I want to look at the same table again, so I guess I have to redraw it here. So I'll draw it a little smaller now. So here's this. Here's my table. And I had the ball rolling across the table. Fine. And we had a coordinate system then that was positive x in that direction and positive y up. Okay, what I did not tell you is that this time, this table is in an elevator. And it is moving up at a rate of 1 meter per second. And over here, observing the elevator moving up, is someone doing another experiment. And they're on the ground. The elevator is moving at 1 meter per second up relative to the person on the ground. So the person on the ground is going to establish their own coordinate system. And what they're going to do is they're going to establish a coordinate system. They're going to call the 0 of their x-axis exactly the height of the ball at t is equal to 0. That's the 0 of the y-axis. They're going to have the positive x go off to the right. They're going to have the positive y up, and they're going to set the 0 of the x-axis then turns out to be about 2 meters away from the edge of the coordinate system that was in the elevator. So now the question is, what is the motion in this new coordinate system? All right, so let's think about what happens. Okay. So first, let's look at the x. At x is equal to 0, that's right here. The ball is 195, well, so 195 centimeters away from the origin. Right, because the origins of the two coordinate systems are 2 meters or 200 centimeters apart. The ball starts 5 centimeters from this origin, so this ball from the 0 is negative 105 is at the position negative 195 centimeters from this from the 0, the origin of the x-axis in my new coordinate system. So x is equal to 1 is negative 185 centimeters. X of 2 is then negative 175 centimeters. And x of 3 is equal to negative 165 centimeters. As it made it 35 centimeters relative to this 0, it's now 165 away from this 0. So if I were to plot this on a graph, what graphical representation? Do you know how I do that? Let me give this to be negative 200, 190, 180, 170, 160, negative 190, negative 180, negative 170. I'm not going to have I'm going to draw that graphically. I'm going to draw sort of a dotted line instead of a straight line because my origin isn't anywhere near what I want to see. And so I would have at 0, it's 195. This is T1, T2, T3. So then it looks like this. The graphical representation of each of those points, negative 185, negative 175, negative 165. And so I still have linearly increasing graph, but a very different x-axis because I have a different origin of my coordinate system. Okay, but what is measured on the y-axis for my new coordinate system? Well, at y is equal to 0, the y position is equal to 0 meters. That's because that's where I set the origin to be. The origin of my y-axis is in line with where the height of the balls the ball is at t is equal to 0. All right, there's only one. I have 4 drawn because the ball is drawn at different points in time. All right, so in 1 second later, I'm just going to erase this. See if this takes... Maybe this is easier or worse than trying to draw over it. And in 1 second later, now the table and so at 1 second later, the ball has moved over to negative 185 on this axis, but now it is up 1 meter along the y-axis. So y of 1 is equal to 1 meter. And so then, let me do this. One second later, the ball has moved over even further now to negative 175 centimeters as measured by this axis, but it's now at 2 meters on the y-axis. So y at t is 2 is 2 meters. And then now I am going to just draw it over. Now at some time later, now the top of the table has moved up here. The ball has moved over here. The ball has moved to its final point, negative 165 on our second axis. It was 35 centimeters on our other axis. But now it has moved to 3 meters on the y-axis. So now if I graph the y as a function of time, the y position is a function of time, 1, 2, 3, and then thankfully, we have 1 meters. It's quite straightforward. 0, 1, 2, 3. The y coordinate of the motion in my second axis now is increasing with a linear slope, which of course is very different than the y-axis from the previous coordinate system. So in this case, I have 2 coordinate systems that are moving at constant velocity relative to each other. And that is something also that we will encounter in this course, but it shows you how important it is that you have to choose a coordinate system, you have to choose your zeros, you have to choose which directions are positive, and then the motion that you see, that is measured, the motion that is measured in those coordinate systems depend on those choices.